Greetings, students. Today I'm going to spend a little time walking you through Chapter 10 on Logistic Regression. So at this point in class, you have obtained the skills to analyze different situations. You can analyze two categorical variables using the tabulate command, and you can analyze interval level dependent variables with the regress command. But today we're going to talk about something a little bit different. We're going to talk about logistic regression. So the first thing you're going to need to do is open up GSS 2012, and I have my handy little do file over here. And I'm just going to take a couple minutes to explain logistic regression. So logistic regression is designed to analyze relationships between independent variables and a binary dependent variable. So up to this point, we've been talking a lot about linearity. Things like what predicts maybe the Obama thermometer, how people feel about President Obama on a scale of 0 to 100, or the Gini coefficient, inequality on a scale of 0 to 100. And these are continuous variables. And so we assume linearity between our independent and our dependent variable. With logistic regression, we can't assume linearity the same way, at least. So with logistic regression, the dependent variable is the same as a dummy variable. It's binary. We look at things like voting. You either voted or you didn't. You support gay marriage or you don't. You live in the South or you don't. You're married or you're not. These are things that you can't be kind of. You can't kind of vote. You can't kind of live in the South. You can't kind of be married. And so we code these variables the same way as we code dummy variables, ones and zeros. And a common dependent variable in in the analysis of political behavior is whether people voted in an election. So in this first step, we're going to look at voting in 2008. And so the first thing I'll show you is the codebook command, which will show us how voting in 2008 is coded. And as you can see, it's a 0 and a 1. You either voted or you didn't. Or your value is missing, which in that case, those respondents will drop out of the model. So it's ones or zeros. And the other thing we're going to use, for an independent variable that is often linked to turnout, is education. In the GSS, education ranges from 0 to 20. 0 is no formal schooling, and 20 is 20 years of education. I'll show you that one too. So here you can see our range is 0 to 20. We have 21 unique values. Our mean education is 13.5, so that would be graduating high school plus a year and a half of college. Yeah. So we would expect our relationship, we're going to model the probability of someone voting with our independent variable being education years. So we would expect a positive relationship between the independent variable and the dependent variable. As education rises, the likelihood of the individual voting also rises. Unlike ordinary least squares, we cannot assume that 1 year change in education is associated with a consistent increase in the probability of voting. So, we can't assume that the effect of education on somebody at the low end of education is the same as it is for somebody with a high level of education with 1 unit of change. You'll see what I'm talking about better later. So what we're looking at is the logged odds of voting is our dependent variable, because that's what logistic regression computes, the logged odds of voting. And your constant is represented by A, and B is the coefficient that represents a change in the logged odds of voting for each year of education. So unfortunately, and I know what you're thinking, what are logged odds? So logistic regression is harder to interpret than linear regression. With linear regression, we have our constant and our coefficients that represent changes in the actual dependent variable. In logistic regression, the constant will tell you the logged odds of voting when education is 0, and the coefficient will estimate the change in the logged odds for each unit change in education. And the problem with that is no one understands what that means. Your mother asks you what's the impact of education on the probability of voting, and you can't say, well, it's an increase in the logged odds of blank. That doesn't make any sense. So we have different ways of figuring out how to make sense of this. So now we're going to talk about the logit command and the logistic command itself. The logit command will display an estimate for a constant, A, and the coefficient, B, both expressed in terms of logged odds of the dependent variable. The logistic command will run the same analysis, but it will express the coefficients in either odds ratios or logged odds. So I will show you this now. So here is the logit command for our model predicting the likelihood of voting. And you can see here's a coefficient. We've got z-score, which is a lot like a t-score, the p-value, pseudo r-squared, which is like an r-squared. It looks a lot like when you run linear regression. And I'll run the other one here. Oops. Logistic. Now this one spits out something a little bit different, as you can see. So we have a coefficient here, and here we have an odds ratio. So let's take a look at the logit model first. The constant is the estimated logged odds of voting for people with no education. So that's what this number represents. And the logged odds of voting increased by 0.226 for each 1 year increase in education, right here. As expected, the independent variable increases, and so does, as the independent variable increases, so does our likelihood of voting. We can tell that by, we've got a positive coefficient, and we've got a p-value less than 0.05. So that part of the interpretation is the same as OLS. However, we don't really know we don't really understand logged odds. So we're going to take a look at the other regression, which gives us odds ratios. So notice we now have odds ratios where the coefficients were. This odds ratio tells you by how much the odds of the dependent variable change for each unit change in the independent variable. An odds ratio of less than 1 says that the odds decrease as the independent variable increases. So we'd have an inverse relationship. An odds ratio equal to 1 says there's no relationship. An odds ratio greater than 1 says that the odds of the dependent variable occurring increase as the independent variable increases. So there's a positive relationship. So again, we can see here we have a statistically significant p-value, pretty large z-score, which is like a t-score, and we have an odds ratio of 1.25. And because it's above 1, it means we have a positive relationship between the years of education and the probability of voting in 2008. So in our model, the odds ratio is 1.25, which means that the respondent at a given level of education is 1.25 times more likely to have voted than a respondent in the next lower level of education. Odds ratios make things a little bit more understandable. They tell you the percentage of change in the odds with each unit of change in the independent variable. In our model, a 1-year increase in education increases the odds of voting by 25%. Remember, 1, if this was a 1, we'd have no relationship. So you're really looking at how far away from 1 is it. If it was under 1, we would have a different, we would have a negative relationship. Since it's over 1 and 1 is no relationship, the odds of the odds increase for each by 25% for each year of education, and that's 0.25, 25%. So the next thing that the book wanted you to look at was iteration. So that's up here. Now, what logistic regression uses is maximum likelihood estimator, MLE. So what Stata will do, it will first try to predict the observed values on the dependent variable without using any independent variables as a predictor. So basically, Stata is going to take a random guess, and it's going to ignore whatever you think goes into the probability of whatever it is you're trying to predict, in this case, voting. And then it's going to bring in the independent variable and run multiple analyses to determine the best predictive fit. And so the idea here is you want this number. So this is iteration 0 is predicting based on just random. And that number, we want to get far away from this number. We want to get close to 0. And as you can see, we didn't get very far before it was spitting out the same number. And we're not very different from just random guessing, which would lead you to conclude that you're missing something in your model. Obviously, we only have one independent variable in this model. There may be other things we would want to control for to predict whether a person votes or not. So another thing I need to draw to your attention is the chi-square. Over here, we have a walled chi-square. This tells us whether our model is significantly better than the know-nothing model, so the model in iteration 1 where we're just randomly guessing. And in this case, our p-value for the model is equal to 0, as you can see here. And so we can conclude that including education as a predictor significantly enhances the prediction performance of our model. And here we have our pseudo r squared, which is this a lot like the r squared in OLS. It's supposed to let you know how well your model explains variance in the dependent variable. And as you can see, we don't have a very high r squared, but we only have one independent variable in our model. So that will happen. So speaking of only having one independent variable, as we move on, we're going to do Logistic regression with multiple independent variables. So other things may play a role in the probability that a person votes. And logistic regression can include, much like linear regression, control variables. And I will show you that right now. Let's see. Okay, so controlling for education, each additional year in age increases the odds of voting by 4%. And we can see that right here in this one with the odds ratios. We're at 1.04. This would round to 4%. The model is statistically significant, so compared to knowing nothing and just randomly guessing on our dependent variable, our model significantly improves our ability to predict the likelihood of voting. You can see education is statistically significant and positive, age is statistically significant and positive, and our pseudo R squared went up quite a bit, pretty much double. So we're doing a better job of predicting voting in the 2008 election with this model. Now, still, the percentage increase with the odds ratios is not ideal for understanding what's going on with this relationship. So what we can do is we can use predicted probabilities. We can use predicted probabilities to answer questions like, controlling for age, what is the effect of a 1 year increase in education on the probability of voting? Logistic regression alone will provide an inconvenient answer. It depends. In logistic regression, the effect of each independent variable on the probability of the dependent variable will depend on the values of the other predictors in the model. So, for example, an additional year of education is going to have a different impact on the probability of voting for someone who is 18 than it is for someone who is 45, and we'll see that later. So we can hold specific independent variables constant by using the margins command. So we run our model right here, and then we use the margins command, and this says this will give us predicted probabilities at education ranging 0 to 20 in increments of 1. So it'll give us 0 years of education through 20 at increments of 1. And it will hold any other variable in the model to the mean. So it'll hold age at the mean. So here we go. There's our model again. Same thing. And it gives us, got to get past some of this, it gives us predicted probabilities. And so this is every year of education, and this is the probability of voting for every year of education. And the age is held at the mean, which in our sample, in the GSS, is almost 48 years old. So we can see what an increase of 1 year of education has on the probability of voting for someone who is roughly 48 years old. And I will point out, you need to notice that the increases in the probability, so you have a 7% chance of voting, or a 9% chance of voting, or 11, then 14, and so on. The probability of voting changes through each year of education. The difference between each year is not consistent. So we're not looking at a linear relationship. So for example, somebody with here's a pretty good jump. Somebody with 9 years of education is 40% likely to turn out to vote. 1 year change, 10 years of education, you're 47%. So that's that's a good 7-point difference. But down here, like you look at, so I'm not 47 years old, but I do have 20 years of education. So if when I go from my 20 years of education to 21, I go from 93%. I mean, assuming I was 48 years old, I'd go from 93% likely to vote to 94, which isn't a very big change at all. So education makes a smaller difference at the top and the bottom of the scale. So let's see. Now, the next thing we're going to do is margins with the over option. Oh no, wait. We're going to take a look at this first. So we can plot. We can do a margin plot of these predicted probabilities using this command here, and this is in your book. So I will run this, and hopefully, if it works, there we go. All right. So this shows the probabilities we just looked at for each year of education, holding the age at the mean. As you can see, we never get below 0, so your probability of voting can't be negative, and we never get fully to 1. But we do have this S curve, and that's what you end up getting when you're looking at probabilities and logistic regression. And you can see that they put a dotted line here through 50%, 0.5, so that you can see where on education does a person become more likely to vote than not. So I'm going to exit out of that. Now I have the margins command with the over option. The margins over option will run the margins command separately, once for each value of a categorical variable specified in the option. So what we're going to do is we're going to generate a new variable, because we want to look at 2 different groups of ages and the probability of voting as education increases. So yeah, let's do that first. So we're going to split up. We're going to do our logistic regression again, and then we're going to create a variable that has age for under 30 and age for over 60 to see what how the probabilities are different for people with education, with a certain level of education under 30, than they are over 60. And so this says age greater than or equal to 60, and age that doesn't equal missing. So we're going to cut out the missing data. So here we go. We created our new variable, and now we're going to use the margins command again, and the over option to figure out how the probability of voting differs between these 2 groups. Okay, so this is going to spit out a lot of stuff. You have to hit more. Okay, so now what you see here is similar to what we just had. However, you get 2 values for every for every year of education. So you have 1 year of education for people under 30 and 1 year of education for people over 60. And as you can see, people over 60 are much more likely to vote with 1 year of education than people under 30 with 1 year of education. And as we scroll down, you can see that we have the same kind of pattern here. We get the probability for people under 30 with the same amount of education as with the probability of people over 60 with the same amount of education. And you can see the differences between the two. So if you wanted to look at the probability of somebody voting in the 2008 election with 20 years of education who's under 30, so somebody like myself, I would be about at a 0.84. But if I were over 60 with the same amount of education, I would be at a 0.97. So, kind of common knowledge in politics that young people are less likely to vote than old people, and even controlling for education, we see that. So, the next thing we want to do is take a look at this. So we can margins plot with the over option. And this code is also in your book. Careful copying it, because you know how it is. If you get one thing wrong, it will yell at you. All right, sweet. Oh. I made it disappear. There it is. Okay, so as you can see, we get two lines in this plot, and they both kind of have that S curve again, never going above 1, never going below 0. And you can see that for our age group, 18 to 30, obviously it's 18 to 30 because you can't vote until you're 18. I don't think there's anybody sampled in the GSS that's under 18. So we have 18 to 30-year-olds, and this is their probability of voting with education. And then we have our group of 60 and older, and this is their probability of voting with certain levels of education. And you can see that they're always, at any given point, more likely to vote than the younger group. In fact, you can see here, at about 5 years of education or so, maybe 6, we hit the 50. You become more likely to vote than not when you're over 60 and you have about 6 years of education. And 18 to 30, you don't become more likely to vote than not until you have about, looks like maybe 12 or 13 years of education. So graduating high school. Yeah. So let's see here. What are we doing next? All right. Okay, so the last part we look at is kind of a hybrid of the first two things we looked at. So we have seen that we can use the @means command to hold our control variables at their means. So that's when we were holding age at like 47.888 something. And then we allow the independent variable to vary. That was our education. We have also seen that we can use the over option to specify a range of interesting variables. That's what we just did with looking at the difference in probability of voting predicted by taking into account education, comparing 18 to 30-year-olds and 60-plus-year-olds. Now I'm going to show you pretty quickly that we can do both of these things together. So sometimes you want to hold options at a certain value. So if I wanted to look at different probabilities for predicted probabilities for voting, and I had gender in my model, I wouldn't really want the model to. I wouldn't want Stata to hold gender at its average, hold it at its mean, because that would be like a 0.5, and that doesn't mean anything. You're male or female. Same thing, yeah, or like earlier, married or whatever, south. Like you don't want certain things to be held at the mean, because you get something that's just in the real world doesn't make any sense. You're not 0.5 of a man, and you're not 0.5 married. So we can hold certain things at the average, and then we can hold other things at values that we want to hold them at because we find that interesting. If I want to compare older women with younger women, I can hold the gender value to a 1 and compare older and younger women and their probability of voting, or whatever we're trying to model. So let's see, we can go ahead and run this then. Now, in this model, we've decided to take into consideration not just education and age, like we did do, but also income. And I think this is a 6-category variable, and that's why it's 006. And then partisanship, which takes the value of 1 if the respondent identifies as a partisan, so a Democrat, a strong Democrat, or a strong Republican. So they're highly partisan people. And we can see in our model here, income is not statistically significant, but partisanship. So if you're more partisan, you're more likely to vote. Not real surprising. Also, if you're older, you're more likely to vote. And if you have more education, you're more likely to vote. These are all positive, as we would expect, and statistically significant. Let's see here. The pseudo R squared has now gone up to 17, 0.17, and the probability that we could predict the likelihood of voting randomly better than this model, well, we can't. So this model is better than random chance. All right. Let's see here. So now they wanted us to take a look at the sum of the variables that we just brought in. You can see here that we have our weight and then our means for these variables, our mins, our max. And we're going to do the margins command to compare these groups at certain values. And what we're going to do is, as you can see, okay, delimit, make sure you put the semicolon at the beginning and the end. Margins if our age variable that we created is not missing, so the exclamation point means is not, doesn't mean you're excited. And then we're using the over option again with the age variable. At education years equals, and that's 0. We want to go 0 to 20, so the full range of our scale in 1-year increments. and we're going to hold income and partisanship at their means. We could make these variables anything. If we wanted to look at people with high incomes, we could pick a high income category. If we wanted to hold people to a different level of partisanship, we could just put a different value in here. It's whatever we want to hold it at. By the way, as a note, I don't know what the 06 means because this mean is obviously higher than 6, which means our variable is not a 6-point scale like I had figured. So let's run this. We'll take a look at that. Okay, so it's gonna spit out a lot of this jargon where it's telling you what it's doing. So we gotta click more. Just a little bit more. There we go. Okay, so now we're getting the probability of voting for, let's see, what would this be? Yeah, our age and our education. So education, age, just like we did before, actually, except now we're holding our income and our partisanship at a specific value. And you get the same 0.05, 0.20. You can see that the changes are different on different points in the scale. So up here, holding income and partisanship at their mean, for a person under 30 with 20 years of education, you have a value of 0.84. Your probability of voting, 84%, 0.84. You are 84% likely to vote. The same person who's older with the same income, so the same income and same partisanship, with the same years of education, but they're over 60, is more likely to vote with a value of 0.96. So you can see that the changes are different in different parts of the scale, and these margins commands make understanding what logistic regression spits out at you much better, makes it much easier. So instead of telling somebody, listing off a coefficient and saying, well, this has a 0.23, a positive 0.23 impact on the logged odds of voting, you can actually tell people what the probability that the person with certain characteristics will turn out to vote is. So this is the final thing that the chapter wanted us to do, and I hope this was helpful. And this concludes the walkthrough of Chapter 10 on logistic regression.